Okay, so it's great that we had this introduction about the motivation for speeding up magnetic RAM. MRAM, Eli, that's magnetic random access memory. And you know, the desire to push that down into the sub-nanosecond switching time. So I can skip over all of that and go right to this. So the physics of magnetic switching that we just heard about has to do with the fact that there's a characteristic frequency associated with making a magnetic layer go from up to down or left to right. And that frequency is called the ferromagnetic resonance frequency or the precession frequency. And Dr. Prévenu spoke about switching in relative to the period of that oscillation. That typically the oscillation frequency is in the neighborhood of 10 to 20 gigahertz. So if you can be really clever, like the previous speaker, you can manage to get the magnet to switch in 1/2 of the oscillation period and get it to damp out and stop on the other side. That's about the best you can hope to do. And that gets you into the range of, let's say, 200 picoseconds or maybe even a little bit less. So up until the period, discovery I'm about to describe to you in 1996, the understanding of how you can switch a magnet was that that is a fundamental speed limit. Now, in 1996, a group in Grenoble, in Strasbourg, did an experiment where they shot a 60 femtosecond laser pulse at a very simple, magnetic thin film of nickel. And I won't go into great detail, but there are ways with laser optics to probe magnetization, and they were able to do that on a time scale of sub-picosecond. And what was discovered was that the magnetization, it didn't switch, but it rapidly collapsed to about 50% of the saturation magnetization in a time scale of on the order of 100 femtoseconds. And this was a great, actually continues to this day to be a great mystery, how you could possibly demagnetize a magnet by this amount in such a short time. Where does all that angular momentum go? It turns out to be quite an interesting theoretical problem. But nevertheless, many groups picked up on this and reproduced it. There was a lot of debate about whether the measurement technique was measuring the right thing. All of those things got resolved. It's now very well accepted that this kind of excitation of a magnetic layer can produce an extremely rapid change in the magnetization. Now, in 2011, an even more remarkable result was published from a group in Nijmegen. And what they showed is that when you shoot a similar femtosecond laser pulse at this material, an alloy of gadolinium iron cobalt, not only does the material demagnetize, but it actually switches. And this is some imaging, magnetic imaging microscopy showing, here's a fully saturated magnetic film of this material, a few 10, 20 nanometers in thickness. And here's a focused laser spot with a diameter of a little less than 20 microns. And after one single shot, the magnetization of this film in the region of where it was exposed to the laser pulse reversed completely. And then when you shot the same layer, the same spot the second time, it switched back. And it alternates back and forth in a fashion we call toggling. And if you saturate the film in the other direction and shoot it with the laser pulse, you see the same kind of toggling back and forth. And remarkably, it is completely independent of the polarization of the laser. It doesn't matter whether the laser is circularly polarized left or right or linear. The same thing happens. Now, the mechanism for this to happen is also under considerable debate. An elegant experiment was done with 100 femtosecond X-ray pulses produced at a synchrotron source in Berlin, and they were able to tune the X-rays individually to the gadolinium magnetization and to the iron. And what was discovered was that the iron demagnetizes much faster than the gadolinium, And there's a very brief moment here where, well, actually I should back up. This material is called a ferrimagnet, and the spins of the gadolinium atoms and the iron atoms form two separate sublattices. The gadolinium ions, the spins all orient in the same direction. The iron spins orient also in the same direction as each other, but anti-parallel to the gadolinium spins. That's a well-known property of this material. It's called a ferrimagnet when you have this property of having two sublattices where the spins orient in the opposite direction. That seems to be critical to this switching phenomenon that was observed. The gadolinium demagnetizes with the excitation by the laser pulse more slowly than the iron. The iron crosses through zero. There's this brief moment where the two spins actually are parallel to each other. The iron goes all the way through zero. That drags the gadolinium to switch back. And at some later time, the system fully recovers to the opposite orientation. And this toggling has to do with the fact that these two sublattices have different dynamics and different magnetizations, and on every laser shot, they both go towards zero and cross. And we're talking about, 100 femtosecond laser pulses, and the dynamics here is that the switching of the two sublattices has basically all happened after the first picosecond. So this looked like an even more exotic and amazing ultrafast dynamics in a magnetic material. And immediately, people started thinking about how to take advantage of this. And most of the community working on this since that time, 2011, has been focused on trying to do some kind of optical memory, which would be extremely fast. And so this is kind of a cartoon that came from the Nijmegen group, sort of showing some kind of replacement for, let's say, magnetic hard drive memories that could somehow go faster. Now, of course, there are some issues with that. First of all, optical memories are kind of already becoming somewhat obsolete because it's very hard to scale the size of a bit down for an optical memory, whereas hard drives are now scaling down into the 20 nanometer range. Also, you need a femtosecond laser for this. That's kind of expensive if you have to have a femtosecond laser inside every disk drive. Now, we looked at all of this, and what we discovered was that, first of all, the best understanding of this physics is that what's happening here is actually all the laser is doing is delivering an extremely short burst of energy to the magnetic material. That is absorbed by the free electrons. This is a metallic material. The electrons get extremely hot for a very short period of time because they are out of equilibrium with the lattice. And so that's the key thing that triggers this, is the heating up of the selective heating of the electrons, which requires very little energy because the heat capacity of the electrons is small compared to the heat capacity of the lattice. So you heat up the electrons to maybe 1,000 degrees, but by this time the lattice and the electrons equilibrate, and the net heating might be only 10, 20, or 30, maybe 50 degrees. So the idea that we thought might be interesting to explore was, could we adapt the physics here in this ultrafast magnetic switching into something that looks more integrable on chip, where instead of using a laser pulse to heat the magnetic layers, electrons, we would use a pure charge current pulse with very short duration. Could we get the same thing to happen? So the first question that we wanted to ask ourselves was, what's the pulse width that's needed for this? If I need 100 femtosecond electrical pulse, I'm probably not going to get that, at least on chip in some kind of realistic integrated technology. But if I can maybe get away with a longer pulse, then perhaps it would work. So we did experiments to look at this gadolinium iron cobalt switching, where we used an optical laser pulse, and this is measuring not the element selective, this is just measuring the net magnetization as a function of time. And we varied the excitation laser pulse duration from 60 femtoseconds to 1 picosecond up to 10 picoseconds. And what we found is that indeed, even for laser pulse duration of 10 picoseconds, the switching still happens. It happens a little bit more slowly, but it still happens. So that was good news. And actually, what was even more surprising, just focus on this red curve, we looked at the total amount of energy density. By the way, there's a minimum critical energy density needed in order to induce this switching. If the laser pulse energy is less than that, you don't get switching. If the laser pulse energy, and that's down here, if the laser pulse energy is above the critical energy density, you do get switching. And this is plotting the minimum energy density from the laser in units of millijoules per square centimeter in order to induce switching. And what we found, to our surprise, was that the energy density needed going from 100 femtoseconds to 15 picoseconds only increased by less than a factor of 2, which was kind of a surprising result. And I don't have time to go into discussion about the understanding of the physics of that. We think we understand it, but I will just take that as a given and move on. So this was really good news. All right, so then the next question was, is it sufficient to just heat up the electrons by some kind of other mechanism other than using a laser pulse? And so we did an experiment, as shown here. We made a stack of a thin layer of gadolinium iron cobalt, and we put a relatively thick layer of gold on top. And this time we shoot the laser at the gold. So what happens here is the laser pulse heats up the electrons in the gold, but the gold absorbs all the laser pulse energy before it gets to the gadolinium iron cobalt layer. So now what we have are essentially a fast current pulse of hot electrons from the gold that then diffuse into the gadolinium iron cobalt. So this was a way of testing whether or not electrical sort of charge current pulses would do the same mechanism. And what we found is, yes, indeed it does. With a layer of gold of 57 nanometers in thickness and a little over 10 nanometer thick gadolinium iron cobalt, we still see the typical toggle switching. And we also measured the time dependence of this, but I'll skip that for interest of time. Basically, it happens as fast. There's a little bit of time delay for the switching, because it takes on the order of a few hundred femtoseconds to a picosecond or so for the electrons to diffuse from the gold into the gadolinium iron cobalt. And that time delay was a clear signature that what we were seeing were basically just electrons flowing into the gadolinium iron cobalt. Okay, so now how do we, so I showed that 10 picosecond duration pulse is probably good enough. How am I going to make a 10 picosecond electrical pulse? That's not easy, but it's doable. Now, the first way of doing it is using a technique developed actually way back in the mid-1980s using very fast photoconductive switches. So you create a gold strip line, and you put it on top of some semiconductor material, put a DC bias on one of the lines. When a laser pulse hits this area between in the gap, it induces, this is an insulating, undoped semiconductor, and when you shoot it with a laser pulse, you create carriers. That induces conductivity. You get a current pulse that shoots from one line to the other, and that launches an electromagnetic pulse down the line. This paper in 1986 actually was able to demonstrate a generation of an electrical pulse running down this line with a duration of less than a picosecond. The measurement is just done right here using the same idea. You have, again, a semiconductor photoconducting switch where you just sample a little bit of the electric field that arrives at this part of the line, send that into essentially a low-frequency detection circuit, and as you vary the time delay between these two pulses, when the pulse just arrives, you get current flowing in here, and this is a high repetition rate experiment, so you get DC current going through here. The semiconductor is specially treated to have a very short carrier lifetime so that once the current starts, it shuts off very fast because the carriers recombine in a very short period of time. This particular one was using a silicon on sapphire layer that was heavily damaged by oxygen implantation. This technique is sometimes called an Austin switch, named after the Dave Austin, who was the one who first essentially proposed this idea for making very short electrical pulses. Now, that sounds pretty exotic. I told you it wasn't very practical to have a laser for an optical memory, a femtosecond laser for an optical memory. Here I'm showing you I need a femtosecond laser again. But actually, in CMOS, the switching speed of CMOS transistors in advanced technologies today is in the picosecond range already. So here is published data. We saw this plot, I think on the first day, yesterday, from Paulo, showing that for Intel's 45 nanometer technology in 2007, the transistor switching delay was about 5 picoseconds. And I think Paulo showed us by the way, this is the last time Intel showed the actual switching delay of their transistors. Since then, they do not report that anymore, but it's relatively easy to extrapolate, as Paolo Gargini did in his first talk of this symposium, that in today's 14 nanometer technologies, this delay is probably 2 picoseconds. If you've got a transistor that switches in 2 picoseconds, you can make a 2 picosecond electrical pulse. So this is definitely integrable on chip, but I don't have easy access to this technology, and to build my magnetic devices on top is quite a challenge. So we went forward and used our Austin switch technology to make a basic proof of concept. So can we, in fact, generate such very short electrical pulses in a conventional wire, deliver that to a magnetic load, and induce this ultra-fast magnetic dynamics? So here's a picture of one of these strip lines. Here's the magnetic load. A little bit farther along on the strip line, not shown in this image, is the photo switch. And the first experiment we did was on a simple magnetic material, essentially platinum cobalt multilayer. And here we show measurements of the electrical pulses. This voltage here is the DC bias voltage applied. And what we see is we're generating electrical pulses with duration on the order of 6 or 7 picoseconds. And what we found is that, this is the data right here, in this simple ferromagnetic layer, we were able to induce ultra-fast demagnetization, like the first experiment I showed you for nickel. And the demagnetization happens on the same time scale as that of the electrical pulse. For comparison, we also used the laser itself to try to demagnetize the same layers, and we see slightly different time dependence of the dynamics of the magnetic material. That's interesting, and you know, if you like to understand our interpretation of why these two curves are a little bit different, you can go to this paper and read about it. Okay, so finally, can we get switching in gadolinium iron cobalt? Well, based on this result, what you notice is we're measuring a demagnetization of only on the order of 1%. So it didn't look like we had enough current to deliver the amount of energy needed to switch the gadolinium iron cobalt, which involves demagnetizing all the way to 0. So we had to do a little bit of work. Here's our Austin switch for this experiment. We worked on scaling it up. So we optimized, or we increased the size of the Austin switch. We went to an amplified laser that delivers more laser pulse energy, a couple of other improvements, and we got this similar structure here, where now the gadolinium iron cobalt is in series with the gold in about a 4 by 5 micron square. It's in both of the strip lines. These results that I'm about to show you are about to appear in Science Advances within the next month. So here's the results. So first of all, just for comparison, this is again showing the optical switching. This is of the same material on the same wafer that I have the electrical circuit on. And here's the electrical switched result. So here's, again, a magnetic image. The gadolinium iron cobalt is in this little square region here, as I showed previously in the optical image. And after a single electrical pulse, both of these squares switch. Another electrical pulse, they switch back, and so forth. It toggles just like the laser-induced switching. And this experiment was done with about a 9 picosecond duration electrical pulse. So this is, I would like to submit as the first demonstration of ultrafast electric current-induced magnetic switching. It's a completely new magnetic switching mechanism. There's no spin torque here. There's no spin orbit torque. There's no polarized current of any kind. This is a purely unpolarized, simple, straightforward charge current. And we're getting this switching. Now, here's the time domain. So we measured how fast the switching occurs. And here you see, for comparison, the laser-induced optical switching. This is the red circles are for an optical pulse of 1 picosecond duration and an energy density of around 1.4 millijoule per square centimeter. If we go to a somewhat longer optical pulse, 6.5 picoseconds, that's these triangles. The switching occurs a little later because the excitation pulse is longer. As I said before, when you increase the laser pulse duration, you have to increase a little bit the amount of energy in the laser. And here's the electrical pulse with a 9 picosecond duration. And we can calculate the energy density delivered to that magnetic resistor because we can measure the electric field, we can measure the total current delivered, and the energy density is very comparable to that needed for optical switching. And sure enough, the electrically excited material crosses through zero and remagnetizes on the other side, again, in a time scale comparable to that of the optical switching. 9 picoseconds seems like it's longer than the optical pulse of 6.5, but we actually chose this one as comparable because the energy being deposited by this electrical current pulse is essentially by joule heating. So the energy delivered is proportional to the current squared. So for a 9 picosecond electrical pulse, the energy delivery has a duration of comparable to this, about 6.5. So you can see that we have been able to successfully demonstrate ultra-fast magnetic switching in under 10 picoseconds. Now, the current density is pretty high here. It's in the well above 10 to the 8 amps per square centimeter. The switching current density for the spin torque switching that we saw in the previous talk is typically a couple orders of magnitude less than this. And you might be worried about some like damage or electromigration. But remember that this is a peak current pulse density in a very short duration of only like 9 picoseconds. This experiment is done by running at high repetition rate with the laser running at about 100 kilohertz repetition rate. And we scan slowly to acquire all this data. There's quite a bit of averaging. We measured many different times and varied various different things. This particular sample was subjected to over 10 to the 10 electrical pulses with no evidence of any kind of degradation. Now, about the energy, this energy density, what does that translate to? Well, if we were to scale down to a 20 nanometer cell in an MRAM with a thickness of also about 20 nanometers, which is the thickness that was used in this experiment, the energy delivered to this scale dot would be 3.5 femtojoules, which again, is very competitive with the STT MRAM results we just heard about. And it would require a switching current to switch a little dot this size of only tens of microamps, which is easily delivered by a single CMOS transistor. Okay, now it's one thing to switch, but in the magnetic memory, you have to also be able to read out. Okay, and the way that you read out is by making a magnetic tunnel junction, which we also just heard about. Typically, with a magnesium oxide tunnel barrier and careful engineering, a magnetoresistance ratio for the two different magnetization states of 200% is achievable and turns out to be perfectly adequate to be able to read out the state of the memory in an MRAM array. Unfortunately, this magnetic material, gadolinium iron cobalt, is not as good for magnetic tunnel junctions. So there's a group at University of Minnesota that's also working on ultrafast switching. ultrafast optical switching, they actually built a magnetic tunnel junction device with a magnesium oxide tunnel barrier, gadolinium iron cobalt magnet, and then as the free layer and a fixed layer of cobalt palladium. They integrated that into an electrical structure and did optical switching experiments. And here's, so first of all, here is the magnetic field-induced switching of this tunnel junction. And what you see is a nice clean separation between the up and down states, a nice square hysteresis loop. Unfortunately, the magnetoresistance ratio for this junction is less than 1%. And that's because this gadolinium iron cobalt does not have the same kind of favorable properties that are very carefully engineered for the magnetic tunnel junctions used in the MRAM technologies we just heard about. So that's a little bit of a challenge. How are we going to read this out if we're switching the gadolinium iron cobalt? And it turns out that so far, this is the only material that has been, this kind of ultrafast switching has been discovered. So what are we going to do? Well, we said, well, can we somehow get a ferromagnet that would give us a much higher TMR, tunneling magnetoresistance ratio? Can we switch that? So we designed the following sample. Here's the gadolinium iron cobalt. Here's a thin platinum spacer, and here's a cobalt ferromagnetic layer. And then so far we've only done optical switching experiments on this stack. The idea here is that the cobalt magnetic layer would be closely coupled to the gadolinium iron cobalt magnetization by what's called exchange interaction. And so the idea was that if we could optically switch the gadolinium iron cobalt, maybe the exchange interaction would drag the ferromagnet on top to also switch. And sure enough, that works. So here are the results, again, just kind of showing you the imaging magnetic microscopy results. And sure enough, when we switch the gadolinium iron cobalt, I don't have time to go through all of the data, but take my word for it, we are confident that the cobalt layer is switching together with the gadolinium iron cobalt optical switching layer. Okay, so with that, I'd like to conclude and give you some perspective. So first of all, we've demonstrated for the first time ultra-fast all-electronic switching of a magnetic material. We've looked at many of the aspects of the physics and the building blocks. We think this opens up really a completely new regime of ultra-fast spintronics, and we think there are possibilities for many new practical applications, including extremely fast magnetic devices for memory and potentially even for logic. Our next steps are going to be to try to, make further progress demonstrating applications. So we're going to, first of all, we're going to build somewhat more complex heterostructures, which we think will allow us to reduce the switching current even further, as well as get rid of this toggle switching. So this is a little bit inconvenient if you have to switch just back and forth every time. You'd really like to be able to just determine which state of the final state of the magnetization you want based on the direction of the current, which is the way the spin-torque MRAM technology works that we've heard about. We think we can do that by using more exotic heterostructures. We're going to try to integrate the electrical readout so we can demonstrate that works. And then integrate these structures on top of high-performance CMOS, which we hopefully can get from Foundry, and completely get rid of the laser and demonstrate that actually, indeed, with a small CMOS transistor, we can actually make this magnetic layer switch. And with that, I'd like to stop and answer questions. And here are my coworkers here at Berkeley and sponsors.
Okay, that's terrific, Jeff. And I wonder if people have composed some questions. And go ahead, please.
So have you thought of a possible pulsed approach to the readout, not just the writing? Did you put any thought into using any kind of pulsed approach to read what you've written?
Okay, so how fast can it be read out is the question. Actually, I think that the readout time is not the limiting factor. So again, as the folks who are developing MRAM are well aware, with a 200% magnetoresistance ratio in a reasonable sized array, they're able to read out in sub-nanosecond times easily. Now, whether or not we want to build this technology into a larger memory array, or whether or not it might be more suitable for the kind of logic and memory applications where we just have small banks of memory kind of interspersed within the logic, is another interesting question that we need to explore.
Can I go into that a little bit further? I mean, it's a fantastic accomplishment to switch the magnet electrically 100 times faster than has ever been done before. But to take full advantage, the magnetoresistance has to also be shown to change very rapidly. So is there some indication that the magnetoresistance can actually change fast enough to keep up with the incredible speed you've shown?
That's a great question. That's an experiment we have yet to do.
Okay.
These are really great results for speed purposes of these devices. I'm surprised that in your plans you don't have characterization of conventional magnetic devices, how much energy they take, the same method you use if you just put different samples, because you're suggesting this material spatial that brought us this speed. What is the level of speed and energy required for the conventional magnetic devices with the same method?
Well, okay. Let me answer this way. The folks at SpinTech, Global Foundries, and others that are developing the conventional memories are measuring those switching energies extremely carefully. We heard some numbers in the previous talk. So I think the way to answer your question is you should be challenging me to measure the switching energy the same way that they do, rather than me have to go and remeasure, some conventional MRAM technology. So that's, I think, a fair demand. And as I say, we're going to try to integrate this stuff right onto Foundry CMOS, and where we'll be able to make essentially a similar measurement.
Okay.
So this is quite beautiful from a materials perspective. What about going from the alloy ferrimagnet to like gadolinium iron superlattices, multi-layers?
Multi-layers. Yeah, great question. I think that's a really interesting and doable idea. Actually, there have been some results using all optical switching that have already shown that layers like that, multi-layers of gadolinium and iron cobalt, can be switched optically. And so far, the switching energies and speeds look similar. It's not clear, exactly how to take greater advantage of this more exotic heterostructure, but it's definitely an extra degree of freedom that we can explore.
Okay, let's thank Jeff Boker again.